continuing on, still on page 86. Now what we're going to do is we're going to exploit what we've just demonstrated through a test to determine the muzzle velocity of a projectile. If we set that projectile up to be fired at an elevation of 0 degrees, perfectly level. Now, here's the thing that we want to keep in mind. Here's a piece of Newtonian physics that everybody walked in here knowing. An object in motion stays in motion until acted upon by an outside unstable force. You walked in knowing that one. Okay, so if we idealize and discount air resistance, and if we discount gravity, if I toss a ball in that direction, it's going to go right in a straight line forever and ever and ever at a uniform velocity, because there would be no force to impede velocity in that direction. If, however, we introduce a force in this direction, it will change the motion of the projectile in this direction, but not that direction. Not that direction. Because, remember, this goes back to this basic Newtonian idea of an object in motion remaining in motion. And if you rode the bus back in junior high, you discovered that anyway. Remember, where was the best place to sit coming home from school or going to school back in junior high? Well, in the back of the bus. Why? Well, because of the bumps. All right, so here's the bus going down the road, all right, and you hit that pothole, boom, bus is going 35 miles an hour in that direction. Your scrawny little ass is going up this way, but staying at the same velocity in the horizontal direction, and you come right back down in the seat, all right? Unless you had Ed Crankshaft driving the bus, and he's looking in the rearview mirror, and he sees you going up in the air, and he waits until you hit apogee and taps the brake, and then you go like that, and he's an orthodontist's dream. But in any event, that's a good demonstration of how an object in motion stays in motion, and the whole idea of uniform velocity along the horizontal axis. So we're going to put all these ideas together. And so how are we going to do this? Well, to determine velocity, back to page 86, we have to go back to how we define velocity. Number one, we define velocity as displacement over time. Right? That's why these definitions are important. Vx, velocity along the x-axis, is going to be stipulated as uniform. Uniform velocity. Just like cruise control. Uniform velocity. V muzzle is going to be set at 0 degrees, and therefore, in that setting, is going to be identical to velocity along the x-axis. In other words, it's kind of a cheat. But cheating's fine, as long as you know how to cheat. Okay, S, in this case, is going to be measured as displacement along the x-axis. As indicated here, displacement along the x-axis. All right. And time is going to be calculated using SY. Why? Because turns out Mother Earth is actually a pretty good clock. If we know how high something is, we know how long it's going to take to hit a certain distance. Okay, so we're going to use Mother Earth as the clock. So we're going to pause here and go to the next page.